We have a graph here, show version with temperature of the pressure of the fixed mass of helium gas trapped in the container with the fixed volume, constant volume. So the graph is a straight line, linear. Question A, deduce whether helium behaves as an ideal gas over the temperature range from 250 Kelvin to 500 Kelvin. Is it ideal and why?
Because the correlation
the graph is a straight line.
Yeah.
Graph is straight line. So the pressure is proportional to the absolute temperature, Kelvin, and therefore this gas is an ideal gas. So stating that is ideal is one grade, and explain a straight line, but not a grade. Question B. Helium has a molar mass of 4 grams. Calculate the mass of the gas in the container. What does it mean by molar mass?
Molar mass is something to calculate
molar mass.
Relative mass.
Molar mass means mass of 1 mole.
Yeah.
So how do we calculate the mass of the gas in the container? What do we have? We have volume, V.
We have volume.
We have a graph. So what does the graph tell us?
Temperature.
What is the equation for ideal gas? P, V equals nRT. R here is the mole number.
Yeah.
Mole. R is an ideal gas constant.
8.31.
Yeah. From this ideal gas equation, we can determine the mole n. Determine the number of mole n. How much gas contained in that container. And multiply this mole with the molar mass, big M, which means the mass of 1 mole, you get the mass of the amount of gas trapped in this container. Okay, so N here is PV over RT, and you can take any value of pressure, P, and volume on the graph. For example, you can take the value here. The pressure is 160 kilopascal, and multiply with 10 to 3 to convert it into Pascal, which means Newton per meter square, and then multiply with the volume given here, 1.0 times 10 negative 3 meter cube PV, and then divide it by the corresponding temperature 400 Kelvin. Okay, and you get the number of mole. So P is 160 times 10 to 3. Multiply with volume 1.10 to minus 3 meter cube, divided by R 8.31, and temperature 400 Kelvin. You have the mole, and then multiply with the molar mass, 4 grams per mole. You will get the mass.
0.19.
Yes, 0.19 grams. Question C. Twice as many helium atoms. So what does it mean? What can we deduce from that statement? Twice as many helium atoms. So we will have double the mole and the mass in the second container. The graph, how does it differ from the first graph?
The pressure increases, so it's shifting to the left.
You use the equation. Should use this equation. PV equal nRT. So for the second container, you have twice the mole, 2n. So the threshold, the same volume. So the threshold will be double. Okay, and as long as it's still an ideal gas, it still follows this law, meaning the graph is still a straight line. Assume the origin. When the temperature is 0 Kelvin, the pressure is also 0, which is not possible. It is impossible, but very close. So the second graph must go through this origin also, meaning we have to change the gradient of the graph. It's passing through 200, but probably twice the gradient. Same origin, but twice the gradient. So that is passing through the 200 kilopascal here. And so we need to explain why it has a different gradient. Try the pressure, twice the number of mole. Try pressure, try number of mole. Just call it P1 and P2. P1 for the first container, P2 for the second container. So this is twice the number of mole. So it's double gradient, twice the gradient, huh? So that at the same temperature, for example, 250 Kelvin, the pressure is twice, meaning 200 kilopascal, okay? At 300 Kelvin, the pressure of the first container is 120. The second container will have twice, meaning 240 here, okay? Straight line, double pressure, meaning twice gradient, and also passes through the origin, okay?